Hello, and welcome to the TI Precision Lab discussing op-amp bandwidth, Part 2. In this video, we'll discuss open and closed loop gain, gain bandwidth product, and quiescent current versus bandwidth. We will also simulate the bandwidth of a circuit and show that it correlates to our calculated results.
The open loop gain, or AOL, of an op-amp represents the gain applied by the amplifier to the voltage difference between the inputs of the device. AOL, for an ideal amplifier, is infinite. Modern real-world op-amps, however, have open-loop gains in excess of 1 million volts per volt, or 120 dB. In order for an amplifier to be useful, negative feedback is required. This is accomplished with RF and R1. Sometimes this is referred to as closing the loop. RF and R1 represent the beta network, or feedback factor, of the op-amp circuit. Beta is a measure of how much of the output voltage, Vout, is fed back to the inverting terminal of the op-amp. In this circuit, we see that RF and R1 create a voltage divider. Therefore, beta is equal to R1 divided by R1 plus RF. In addition to the open loop gain of the op-amp, we now have what is called the closed loop gain, or ACL, of the op-amp circuit. The equation for ACL is AOL divided by 1 plus AOL times beta, where AOL times beta is known as the loop gain. This equation can be rearranged as shown. The closed loop gain equation can be simplified for very large values of loop gain, or AOL times beta. Looking at the loop gain equation, you can see that as AOL times beta increases toward infinity, you can ignore the 1 in the denominator. This leaves AOL divided by AOL times beta. The AOL terms will cancel, leaving only 1 divided by beta. Substituting the equation for beta from above yields a closed loop gain of 1 plus RF divided by R1. This is the common closed loop gain formula for a non-inverting amplifier. The main point to understand is that this equation is only true for very high values of loop gain. Later, we will see what happens for low values of loop gain. In the real world, however, the open loop gain of an op-amp has a low frequency or dominant pole. This can be thought of as an RC filter, as shown here. This simulation depicts the open loop gain of a real-world op-amp. At DC, or low frequencies, AOL is very large. In this case, it is 120 dB, or 1 million volts per volt. As frequency increases, AOL decreases at a rate of minus 20 dB per decade. We see that at 10 MHz, the open loop gain is 0 dB, or 1 volt per volt. Now that we understand that the open loop gain decreases with frequency, how does that affect our closed loop gain? Recall that the term AOL times beta is known as loop gain. If we plot the open loop and 1 over beta on a logarithmic axis, loop gain is the difference between the two curves. The mathematical proof that loop gain is AOL minus 1 over beta on a logarithmic curve is given at the bottom of this slide. In this example, 1 over beta is shown as a horizontal dashed line at 20 dB. Notice that closed loop gain follows 1 over beta for low frequencies, but follows the AOL curve at higher frequencies. Also notice that the point at which the 1 over beta curve intersects the AOL curve is the closed loop bandwidth. Let's take a deeper look at the reasons why closed loop gain follows 1 over beta for low frequencies and follows AOL at higher frequencies. At low frequencies, loop gain, or AOL beta, is large. Remember that closed loop gain is AOL divided by 1 plus AOL beta. So for large values of AOL beta, you can ignore the 1 term. This leaves AOL divided by AOL times beta, and the AOL terms will cancel. Thus, the closed loop gain for large values of AOL times beta is approximately equal to 1 over beta. In this case, 1 over beta is the familiar gain equation of a non-inverting amplifier, 1 plus RF divided by R1. At high frequencies, AOL times beta is small. Remember that closed loop gain is AOL divided by 1 plus AOL beta. So for small values of AOL beta, you can ignore the AOL beta term. This leaves AOL divided by 1, or just AOL. Thus, the closed loop gain follows the AOL curve for small values of AOL beta. We define the bandwidth of the circuit as the frequency at which the 1 over beta and AOL curves intersect. So given the AOL curve from an op-amp datasheet, you can approximate the bandwidth of your circuit for the desired closed-loop gain. However, notice that the x-axis is logarithmic. Therefore, graphically determining the bandwidth can be inaccurate. Another approach to determining bandwidth is to use the gain bandwidth product specification from an op-amp datasheet. The gain bandwidth product is literally the product of the linear gain and the bandwidth. Therefore, you can solve for one of the variables given the other two. For example, let's calculate the bandwidth of a circuit that uses the OPA 827 and a gain of 100 volts per volt. From the datasheet, we see that the gain bandwidth product is 22 MHz. Solving the gain bandwidth equation for bandwidth tells us that the bandwidth is the gain bandwidth product divided by the linear gain. Dividing the OPA 827 gain bandwidth product of 22 MHz by the circuit gain of 100 volts per volt yields a bandwidth of 220 kHz. This calculation is verified by looking at the OPA 827 open loop gain curve from the datasheet. If we draw a horizontal line at the closed loop gain of 100 volts per volt, or 40 dB, until it intersects AOL, we find the corresponding bandwidth is approximately 200 kHz. Notice that solved graphically, you may incorrectly interpret the bandwidth to be 200 kHz, though by calculation we found it to be 220 kHz. It should be noted that the calculation approach to solving for bandwidth is only valid if the AOL curve decreases at a constant rate of 20 dB per decade. While this is true for most op-amps, there are some that have a limited range where the gain bandwidth product is specified. Also, consider that the datasheet gives only the typical value for both the gain bandwidth product and AOL curve. Generally, you can expect a variation of as much as plus minus 30% from this value at room temperature, and an additional error of plus minus 30% over the specified temperature range. So it is always advisable to include margin in your design when considering amplifier bandwidth. Now let's compare a calculation to a TINA TI simulation. Here we have an OPA 140 in a non-inverting amplifier configuration with a closed loop gain of 100 volts per volt, or 40 dB. The OPA 140 has a gain bandwidth product of 11 MHz. Given that our closed loop gain is 100 volts per volt, we find that the calculated bandwidth is 110 kHz. Here we simulate the closed loop bandwidth of the given circuit. At the minus 3 dB point, or 37 dB, the simulated bandwidth is 118 kHz. Though not exact, we have correlation between our calculated and simulated results. Finally, let's look at a number of op-amps that depict a range of gain bandwidth products and their corresponding quiescent current, or IQ. In the slide, we list gain bandwidth products for different amplifiers that range from 12 kHz to 600 MHz. The OPA 369, for example, is a very low bandwidth amplifier. This device is designed specifically to have a very low quiescent current of 0.8 microamps and is called a micro power device. It is more common for amplifiers to have bandwidth in the range of 1 MHz, like the OPA 277. Some amplifiers, like the OPA 350 and OPA 211, have wider bandwidth to facilitate driving A to D converters and for other wide bandwidth applications. For very high speed applications, the OPA 835 and 847 can be used. In general, the wider bandwidth op-amps require more quiescent current. However, there are some exceptions, as displayed by the OPA 835. So why are bandwidth and quiescent current directly related? Let's take a look at the physics relationships for both bipolar and CMOS transistors. Please note that it is not critical to get a deep understanding of the transistor theory to understand amplifier bandwidth. The point here is to show that there are underlying physics principles that relate amplifier bandwidth to quiescent current. If we look at the transconductance, or current gain, of a bipolar transistor and a MOSFET, we see that it is directly related to the collector and drain currents, respectively. Inverting the transconductance yields the impedance, or RGM. RGM is the dynamic output impedance of the first stage inside the op-amp. This output impedance drives the Miller capacitance, CC. The series combination of RGM and CC form a low-pass filter. This low-pass filter is the dominant pole inside the amplifier that sets the bandwidth. In fact, you can see that the third equation down is just another form of the traditional RC bandwidth equation, where bandwidth equals 1 divided by 2 pi RC. In the final equation, we substitute the original GM equation to show how bandwidth is related to GM. This relationship shows that increasing current consumption directly increases the bandwidth of the bipolar op-amp. For a MOSFET, however, the bandwidth will increase proportionally to the square root of the drain current, ID. Therefore, MOSFET devices require a greater increase in current than bipolar in order to increase the bandwidth. In summary, this video discussed open and closed loop gain, gain bandwidth product, and quiescent current versus bandwidth. We also simulated the bandwidth of a circuit and showed that it correlated to our calculated results. Thank you for your time. Please try the quiz to check your understanding of this video's content.